Welcome to all of my students. So today I will continue lecture number 23, and today we will discuss about the regular D classes, regular semigroup and regular D classes, and some very important results regarding that. Now let's start. Let S be a semigroup an element A belongs to S is called regular if there exists X belongs to S such that A is equal to AXA. So element A in a semigroup is said to be regular if there exists some X in S such that A is equal to AXA. And if every element of semigroup is regular, then semigroup is called regular semigroup. A semigroup is said to be regular semigroup if each element is regular. Correct. What are the examples? You take any example of group. Group is always a regular semigroup, correct? So take any example of group. You just write remark. Remark 1. Groups are regular semigroups because every element you can write as A is equal to A inverse into A, correct? You see, you can write like this: A equal to A into E. E is the identity of the group, so it is written as A inverse A. So it means there exists some element in S such that A is written as AXA, correct? So groups are regular semigroups, and also rectangular band is a regular semigroup. Correct. Now, also there is one example. For any non-empty set, you take tau x, that is a set of collection of all maps. So collection of all maps forms a semigroup. We know that, isn't it? This is called transformation semigroups. It consists of all maps from X to X. F is a map. So this is also an example. Tau x with composition, isn't it? Is a regular semigroup. So this is also an example of a regular semigroup. This is called full transformation semigroup. That is the set of all maps from X into X1, X to X. Now we do proposition. Proposition number is, I think, 2.3.1. If A is a regular element of a semigroup S, if A is a regular element of a semigroup S, then every element of dA is regular. See, this is D is equivalence relations. dA is what? Equivalence class. This is the class of D, dA. So if A is regular, then every element of dA is regular. Correct? Means that see, this is the D class. This is D class. This is for this example, this is A, and this is RA. Correct? So if A is regular, then every element of dA is regular, isn't it? So if there is element here, then this element will be regular, this element will be regular, this element will be regular. Every element of dA, isn't it? Every element in the class of dA is regular. Whole D class is regular. The D class. So in this way, if we have to prove, so what we do, we take any arbitrary element of dA. We take any arbitrary element of dA and we show that it is regular. If it is regular, then it means every element of dA is regular. Proof. So take any x belongs to D, isn't it? That is xdA, which implies that XL composition RA, or you can say XR composition LA right. Take any B belongs to D. BDA. BDA, so ALCRB. AL's composition. B, it implies there exists C belongs to S such that A, L, C and C are B. Because A, comma B belongs to L composition R, it means there exists in between C belongs to S such that A, L, C and C are B. This we have, correct? What is our claim? Claim is what? Claim is B is regular. This we have to prove, correct? To prove B is regular, what we have to do? We have to prove there exists some Y in S such that B is equal to BYB, like that. So we have to search, we have to find an element Y in S such that B is equal to BYB. BYB should be is equal to B. It should come like that. So this we have ALC and CRB. We will use all these. So we have ALC. So there exist UVZT belonging to S1 such that UA is equal to C, VC is equal to A, CZ is equal to B, and BT is equal to C. Isn't it? It is, isn't it? Why? Because you see A and C are related to each other. So there exists UV such that UA is equal to C from the left side, VC is equal to A. And when C and B are connected, then there exists some Z and T. CZ is equal to B and BT is equal to C. Correct? So these things we have. Now let y is equal to txv. Txv. Now we show that now byb, we calculate byb. Before this, one thing more, that as a is regular, so we use also this. As a is regular, there exists some x belonging to s such that a is equal to what? Axa. So since we write like this, since a is regular, so there exists x belongs to s such that a is equal to what? Axa. This we also have, correct? Now we calculate byb, btxv into b, correct? Now what is bt? It is c x v so we put the value here. C bt is what? C, correct? And x v, we put the value of b here, that is cz, correct? Cz. So c is what? C is ua x v, vc is what? Vc is what? Az. And what is axa? Axa is what? A. Uaz. And what is ua is what? Cz. Cz is what? B. So we have proved b by b is equal to b. It means that, it implies what? B is regular. And it implies that dA is regular. Remember, dA is regular. Why? Because its every element is regular. We have proved that every element of dA is regular, but it does not mean that dA is a regular sub-semigroup, because dA is what? Basically dA is what? Subset of S. It is equivalence class. It is subset of S, isn't it? And its every element is regular. We have proved, because arbitrary element is regular, so every element is regular. So in this way we have proved. So it means that, what is the conclusion? If any element of D class is regular, then all elements are regular. This is the conclusion. And such D classes are known as regular D classes. You can write like this as a remark. Such D classes are called regular D classes. Such D classes are called regular D classes, correct? Now we move to next proposition 2.3.2. In a regular D class, each L class and each R class contains at least one idempotent. Contains at least one idempotent. So in a regular class, we are talking about a regular D class. In a regular D class, we know that in every D class, columns represents L classes, rows represents R classes. So it's basically a union of L classes and R classes, correct? So we have to prove that each L class and each R class contain at least one idempotent, correct? Okay. And we also know that in regular D class, every element is regular, correct? Consider regular D class dA equals yes. Of course, A is regular. Now we know that since A is regular, therefore there exists X belongs to S such that A equal to what? AXA, correct? Now so see. A equal to AXA, correct? Now what is the value of AX square? AX into AX. Now it is what? AX. So it means that AX is idempotent. Now calculate XA square. XA square is XA. Now AXA is what? So XA is idempotent. So AX is idempotent, X is idempotent. And now you see that AX into A we get as A, and A into X we get AX, correct? What does it implies? It implies that A and AX are related to each other. That is, AX belongs to RA, which implies that RA contains idempotent AX. In a similar fashion, you see A into XA is equal to A, and X into A is equal to XA. So what does it implies? It implies that ALXA, A and XA are L related to each other, isn't it? That is, XA belongs to LA. That is, XA belongs to LA. It implies that LA contains idempotent XA. So in this way, we have proved that each D class and each R class contains idempotent, because this is arbitrary class DA. If you take DB, same will happen. LB and RB will contain idempotent. If you take in DC, then again RC and LC will contain an idempotent, isn't it? Like this CX and XC, this CY and YC. So in this way, we have proved that and also one thing we can conclude from here, see, it implies, just for the sake of knowledge, that is AX and LA are XA, isn't it? means L composition R, and L composition R means D. That is AX DXA. These two atom potents are D related to each other. Now we prove. Now we move to next proposition. Proposition 2.3.3. So every atom potent E in a semigroup is a left identity for Re and right identity for Le. Correct? We have to prove this. So okay. So we'll take any element in X. Take any X belongs to Re. Correct?